Thank you, Ravi, for your introduction. Good morning, everyone. I'm Junrui, a PhD candidate from University of Auckland, New Zealand, and it's truly a pleasure to be here today to present our latest work, which is introduce the proposed design method for larger sized externally bonded fiber-reinforced polymer for reinforced concrete strengthening. Yeah, considering this endeavor has been a collaborative effort, so I'm honored to acknowledge the invaluable contribution from my supervisor, Dr. Enrique de Castillo, Ravi, principal at Kiev Structures, and Aniki, senior R&D manager at Zhang and Rem, who currently pursuing his master's degree at Virginia Tech. Before we delve into the preliminary findings of our project, I'd like to introduce a little bit about the introduction and motivation of our project, basically by some analogies and case studies, to better understand what we are doing for the project and we are doing this. Okay. Unexpected strength. Well, I'm a gym guy. I really into bodybuilding. I doing weightlifting almost every day. That's make me become a type of person that thinks everything around me, in comparison to gym workout. Okay, let me share some thoughts about this topic related to the bench press. Well, when we're doing the bench press, our chest on the tension and the tricep on the tension, and there is an accessory in the gym called muscle patches, and it's quite like a tension tie. We put that on our target muscle. It can help us to push much heavier weight. And akin to how construction installation, they are quite similar thing. It ensures easy application while maximizing the tension for our concrete members. And it provides necessary support for optimal training while without not unnecessary strain on our muscles, the reinforced concrete. So through these analogies, I at least myself understand the project, what is project much better, just by fine-tuning the details for peak performance of reinforced concrete and by using the EB-FRP strategy. Then here is a case study from a heritage building in Auckland region. And actually, I'm serving for a very large project, which is seismic strengthening for concrete diaphragm. But I'm only responsible for a small part of this project, which is FRP tension ties for strengthening. Let's say the figures on the left. It's a concrete diaphragm floor before the FRP installed. The concrete covered breakout and the steel reinforcement exposure to the environment, which compromise the tension capacity of the concrete floor. And move to the right, the floor was strengthened by transverse and longitudinal direction of fiber-reinforced polymer by using the EB-FRP strategy. Everything looks much better. The concrete floor surface was repaired and the strengthening capacity enhanced. But what draw our attention here is, in real in-situ construction scenario, we're often using larger size FRP with the thicker and the longer, even 20 meters. But in our research, we only conduct with tests with quite small scale, maybe no more than half meter. So we just wondering if those two have a really big difference in terms of the influence to overall performance of the strengthening. So we conduct a systematic literature review to better understand this question. We collect over 1,600 data after cleaning. Entire process went through with 5 phases with 2 reviewers. Also, based on some specific criteria to narrow down the range of searching for papers. Then we put those 5 potential variables here, but we primarily focus on those 2 for the size effect. Sorry. I know many of you are more familiar with the American units. I'm doing my PhD in New Zealand, so we're using metric more. But I will convert them to US units in some cases. And for here, the thickness is around 0.006 or 7 inches, and for the length, it's no more than 8 inches. And so for the layer, it's for the thickness, maybe only using 1 layer for most of the cases. So I will using the layers in the further talking about the thickness. Then this also emphasized that for the current test, they are more using with a small scale test, and the need for further investigation with a larger scale EB-FRP system is still needed. Yes. And here is another evidence from my supervisor. This paper was published a couple of years ago, primarily talking about the current available codes and guidelines doesn't always work for predicting or designing the Debond strength from EB-FRP systems, especially for larger size types. Yeah. And build on those evidence, we got confidence to move to the second phase of our project. We conduct 51 experimental works at Simpson Strong Type, Stockton Research Lab. And with the concrete compressive strength from 2,500 to 6,000 psi, with bonded lengths from range of 12 inches to 60 inches, and we're using 1 layer to equivalent to about 12 layers. Yeah. So using 0.02 inches to 0.24 inches. And after all tests done, we get valid results from 48 tests. Because there is another 3 was failed by some unexpected reason, like installation error, etc. And here is our test setup. We can clearly say that the spaceman was anchored by steel frame, and the load cell helped to pull the FRP ties up, and the actuator transfer the data and displacement data to computers. And we also adopt 2 cameras here for 3D DSC, serving as a data acquisition system, and also help us to measure all the plane deformation if they happen. And we attach the targets and rulers for better calibrate the results from 3D DSC system. Okay, now we move to the debond mechanism. It's one of primary funding of our research. We can see a video here. I will play it later and introduce a little bit. It combined with the DIC strand map with the response of load and displacement. And in this case, there's concrete blocks with FRP attached to it, and those black dots are targets I mentioned on the last slide. It's marking the line between concrete and FRP. And we're going to put in the way up from the top of video. If you want to see the sketch of that placement, you also can see the drawing on the upper right corner. We're going to put the way up from top of the video, and then the color will start changing. We are calculated with vertical direction strength. It's the same direction with fiber and the loading. The blue being 0, as it approaches to green and yellow, it increases up to 1.5%. Okay, without further ado, we can get started to see what did the behavior look like. Okay, we can say that in the initial stage, it's a completely elastic up to a certain point when FRP ties start debond. And we can also say that the string active bond zone from the loaded end moves down to the free end direction. The strain also has increased. Because we are using the long type for this case, so we will create a longer panel here. We call it post-debonding deformation. And if it was a short type, it will completely debond very rapidly. Just drop down. Let's say what continue. That's what I'm seeing from this video. And then it's another two typical load displacement response, another two group. Because of the page limited, so we didn't put all of them, only put two typical groups. From the first number in the legend is concrete compressive strength. The 19 is 2,500 psi, and for the 36 is 5,000 psi. And for the next number in the legend is the bonding length, and third one is the layers we're using for our test. We can clearly see the change from these two groups. That is the thicker type, the stiffer type always can provide the higher load carrying capacity. And for the longer type, we can find the longer plateau, serving as a post-debonding deformation. And the third one is more intriguingly, it's about concrete compressive strength. We didn't find we just found concrete compressive strength doesn't play a really significant role for our test. We assume that might be because we're using really limited range of the concrete compressive strength. And in this slide, we just showed what we contribute for the overall database, because we collect the database during the systematic literature review. And that's the earlier part, and for our part is in the red box here. To some extent, we contribute the data to filling the previous empty area for the test with a larger size configuration. Then we move to the failure patterns. All the tests was filled by debonding. So we can compare all the three different parameters under the same condition. On the left, we compared two parameters. One is concrete compressive strength, another is bonding length. We didn't see really clear change for the bonding length, but see clear change for the concrete compressive strength. For the lower concrete compressive strength, it always attached on the FRP more compared to the higher one after debonding. And similar phenomena we observed from the thicker types. For the thicker types, attached more compared to the thinner one. So that inspired us. The debond strength may not only correlate to concrete property or FRP property, but might correlate with those relationship of between two. Then we, based on our hypothesis and the things inspired, we proposed our first model, the predictive model. We first initially want to plot a scatter plot for debond strain and the ratio of stiffness of FRP and concrete. But we find a nonlinear trend there. So we're using the turkey fence method to help us to remove the outliers that are unreliable. Then using the regression algorithm to get a fast fitting curve. Then we get this nonlinear powered relationship for our predictive model. We also did a verification of the data. We tried to compare the data with actual data with our calculated predictive data. Then it shows relatively good correlation here. Then, based on our predicted data, we also want to propose another design data for the designing for the industrial. So we're using the iterative calculation to help us make all over 95% data over the 1-1 line, above the 1-1 line, and maintain those data in a safe and reliable range. Then we propose our second model here. It's for design. Okay, here is some conclusion for takeaway. Primarily from three different aspects. The first aspect is for the set effect. We found that thicker ties always with a higher load carrying capacity, and for the longer ties, it have greater post-debonding deformations. And the second aspect is from a material level. We only say a certain correlation of the concrete with debonding strength. Similarly, was bounded from the bonding length. And the third aspect is our proposed model. The debond strain and the a ratio of stiffness of FRP and concrete have a non-linear and power relationship. And after we compared with actual data and with our predicted data, it shows relatively good agreement. Now, those are the references we studied and used in our paper and during our presentation. Really appreciate their contributions here. And here is another acknowledgement to my financial support and and help from the lab. Many thanks to financial support from from my supervisor through the MBIE Smart Idea and the University of Auckland. Also really appreciate the help from Think Strong Thai Research Lab in Stockton and the material supply from KL Structures. That's all from my presentation. Thank you.